Um, Hi, everyone. Yeah, I'm Joey Murphy. I'm a PhD student at UC Santa Cruz working with Natalie Battaglia. I do Doppler follow-up of transiting exoplanets. And for the past couple of years, I've done that work mostly with the Test Keck survey, or TKS, which you heard a lot about from Alex's great talk yesterday. Um, so today I'm going to give you kind of a rundown of 12 planets from 8 different systems that we monitored with Keck and with APF through TKS. And that's going to be kind of the first part of the talk. And then in the second part of the talk, I have this vague subtitle up here. I'm going to try to sort of explore the post-test discovery era of Doppler monitoring of transiting planets and sort of talk about some principles I think we should keep in mind moving forward. I think Keck and KPF especially has a potentially very exciting role to play in the next decade or multiple decades of Doppler monitoring. Okay. So just again, to give you a reminder, these are all the great people that make up TKS, just to give you a sense of the kind of human capital involved in this large-scale Doppler monitoring effort with Keck. And this doesn't even include all of the OAs and SAs and day crew and admin staff and everybody that makes Keck Observatory hum. So thank you so much to all those amazing people. All right, so I don't have time to go through all 8 systems and 12 planets, but just to give you a lightning fast kind of overview and sense of their orbital architectures, these planets were all observed as part of the planet atmosphere science case for TKS. Why do you need planet masses? How do those relate to planet atmospheres? Well, for small planets like sub-Neptunes, there's a degeneracy in the transmission spectra between planet surface gravity and atmospheric metallicity. And the way you break that degeneracy is by measuring a very precise 5 sigma planet mass. And so a lot of the systems in this science case are sub-Neptunes orbiting G-dwarf hosts. And that was kind of the results of our target selection algorithm that made a compromise between observability with JWST and the economics of measuring all of these precise masses. So I will just, we have to show a little bit of data in this talk. So I'm going to give a spotlight for one system, TOI 1736, which is actually a slightly evolved G-star with a transiting sub-Neptune at 7 days. And then revealed by our Doppler monitoring, there's also a super Jovian mass planet at 570 days at a balmy 270 degrees Kelvin equilibrium temperature, with an eccentricity of 0.37. So if that wasn't enough, there's also a long-term Doppler trend in the system indicative of some distant massive companion that's also lurking out there. So here's the photometry from TESS. And I fit this simultaneously with the RVs using this custom modeling framework that's now publicly available online, and there will be a link to find the code at the end. But I just love looking at this Doppler time series, and it really emphasizes the beautiful synergy between Keck and APF. This star is at a pretty high declination, so when it turned out to be actually periastron passage for the super Jovian planet, it was unobservable from Mauna Kea, but APF was able to fill in all of these points and really help constrain the orbit of the giant planet. So that's just one of the systems here. The sort of culmination of the work in the paper is to put all of the transiting planets in the mass radius diagram. So this is what the mass radius diagram looks for sub-Neptunes. And so I'm showing the planets that we characterize in the paper as the stars. Some of them are labeled, and then underneath them are observations from, or measurements from the NASA Exoplanet Archive as it stood last week. There's a lot going on in this diagram. Just a couple takeaway points, I think, are one, the sub-Neptune regime. You can kind of clearly see the mode of the sub-Neptune regime in the mass radius plane here is host to a confluence of theoretical models of bulk planet composition, right? So it's difficult to disambiguate the composition of these planets with mass and radius measurements alone. That's why we need transmission spectra. Um, and then the other point is just that this mass radius diagram looks so much more filled in than even just 5 years ago, and that's all thanks to TESS. And now with Keck CPS refining the stellar property host for Kepler stars revealed the planet radius valley. So we're thinking about planet demographics in one dimension. Now we're starting to enter an era where we can think about planet demographics in multiple dimensions, and especially the mass radius plane. So, I could stare at this diagram all day long and fit different lines and shapes to it with my eye, but maybe there's a hint of a donut hole for the planet radius valley, in the mass radius plane, and certainly you can see the drop-off in planets after the planet radius cliff above about 3 Earth radius. So lots to unpack here, and we'll talk a little bit more about it in a couple slides. And I promised that the planets we were following up for this SC3 program within TKS were amenable to atmospheric characterization later on. This is a plot of orbital period, and then the transmission spectroscopy metric, which is essentially just a JWST observability metric. Higher TSM means it's better to observe with JWST. And then the color bar is host star metallicity. And so you can see a lot of the diamonds and then stars are doing pretty well in terms of their transmission spectroscopy metrics. So hopefully they'll make great maybe cycle 3 targets. All right, so just want to sort of transition to the next part of this talk in the time that I have left, and that's thinking about Doppler follow-up in the post-TESS discovery era. I was having a conversation with Raphael Luque at OWL at UC Santa Cruz a couple months ago, and sort of he mentioned this to me, and I had this realization. I was like, oh no. He said something like the age of transits is almost over. I was like, oh God. TESS has already looked at the entire sky. It's already discovered all of the sub-Neptunes transiting the nearest and brightest stars, the ones most amenable to Doppler follow-up, right? It's already looked at the sky multiple times. We're not going to get more transiting sub-Neptunes. And so we really have to focus on, one, refining the masses of the small planets that we already know about. 2, verifying the masses of existing planets in the literature, say maybe ones that were confirmed with only a handful of RVs. And then 3, increasing the number of precisely characterized sub-Neptunes in the mass radius diagram. And we have to do all of this with the clock ticking because JWST is only getting older, and we want to get as many sub-Neptune transmission spectra as we can before it's done. So here's the mass radius diagram again. I've just removed the planets from our paper for clarity. And yeah, as of last week, there are about 300 planets smaller than 4.5 Earth radius. And those are all planets that have at least a 2 sigma mass measurement on the archive. So not all of them are going to be your best candidate right now without more follow-up for atmospheric observations, but at least they have something better than an upper limit. And then this is what happens if you remove all of the TESS discoveries. So just kind of going back and forth, TESS has really filled out this diagram in the past handful of years and contributed over 1/3 of all the planets smaller than 4.5 Earth radius. So what can you do with all of these TESS discoveries? So this is a result some of you may be familiar with. Maybe a little bit the source of some debate also. This is Raphael Luque and Enrique Payet presenting evidence of a potential bifurcation in the mass radius distribution of small transiting planets around M-dwarf hosts. So this was, they presented as evidence of these so-called water worlds that are ice-rich planets that follow a 50% ice, 50% silicate composition curve, and then planets with more of an Earth-like composition. So this would have big implications for planet formation and evolution around M-dwarfs. And this work was only really done by refining the masses of radii for 9 planets and 7 different systems, all of which were discovered by TESS. So this is a tangible result of the impact that TESS's discovery and all of the TFOP follow-up has produced. So that was the precise, or the refine aspect of my kind of 3 points here. We want to refine planet mass measurements to reveal these potential interesting science results. Another aspect is to verify. So this is a mass radius diagram again, but these are results just from observations with high res last semester. The squares are previous mass measurements and upper limits from the literature for these handful of planets, and then the white lines to the stars show you the updated mass measurement that we have for these planets after adding more Doppler follow-up in 2023A. So, you know, the masses of these planets and the upper limits are moving around. Some of these are systems that have hundreds of RVs, like Kepler 538b, so it's nice to know that its mass isn't going to move that much. But others, like HD 119130b, you know, this was a planet that had a purported 5 sigma mass measurement, but it was unusually dense. You know, it was like 24 Earth masses. It was only confirmed with 18 RVs, so we continued follow-up, and now it snaps right to the mode of the sub-Neptune distribution. So, so this is what we're saying, and we need to maybe think about going back to some of those earlier RV systems and really ensuring that the accuracy, not just the precision of the masses, is there. And then increase, you know, there are, as I mentioned before, JWST is not going to live forever. In cycle 1, it observed about 35 sub-Neptunes with transmission spectroscopy measurements. TESS follow-up is measuring about 25 sub-Neptune masses every year. And just a cursory inspection of the TOI catalog shows that there are still about 500, that being sort of an upper limit, 500 sub-Neptune size TESS planet candidates amenable to future atmospheric characterization that don't have a mass measurement. So we really need to work on and focus making sure we get masses for all of these, because we're not going to get any more of them. And just to say that we saw this figure yesterday from Alex's talk, but we know from TKS that measuring the masses up to 5 sigma precision with RVs is difficult work. So this is really going to take a community-wide effort, and it's going to be really exciting to see what KPF and cadence observations with Keck are going to do for that. I'll just leave up my takeaway points and take any questions.